In this video, we're going to do about redox, that is standing for reduction and oxidation. We're going to talk about the movement of electrons and reduction and oxidation. We're going to do some reactions to show how you can see the movement of electrons. We're going to use a term called oxidation numbers to assign oxidation and reduction as well. So oxidation and reduction. It is the gain or supply of oxygen for oxidation and the loss of electrons. So really important, you can add oxygen at the same time lose electrons. Okay. Now if we do reduction, it is losing electron. Now a really important point is that it's gaining hydrogen. So sometimes it can gain hydrogen, and because of both of those it will gain electrons as well. But the main thing, because we've done it in orange here, is that it is loss of electrons and gain of electrons. Now this is remembered in a mnemonic which is really familiar in all A-level courses, which is oil rig. Now oil rig stands for oxidation is loss of electrons and reduction is gain of electrons. So if I then go across, oxidation is loss and reduction is gain. Now the really important thing I emphasize here is of electrons. Okay, so make sure when you're writing out your exam answers you put of electrons, don't just put gain and loss. Now, let's start off with redox reactions and common examples of redox reactions. So we've got magnesium plus chlorine goes to magnesium chloride, and we've got our reaction here. Now, the easiest way to find out what's happening in terms of electrons before we go into oxidation numbers is to look at this and go, well, let's look at the ions and let's look at the charges and let's look at the elements. So elements tend to have no charge. Okay, so that means because they have the same number of protons and neutrons. So we're going to do the first one. We're going to split it up into half equations and then look at the charges and how they change. So magnesium is an element, therefore it's 0. So if I write out a half equation, I can go Mg, okay, which is going to go to Mg, and it's important here that you can recognize this is an ionic compound, and therefore this is Mg2+. Okay, and then that means it's gone from there to there, therefore it must have lost 2 electrons. Okay, so we always put the electrons on the right hand side if we're losing electrons. So if we're losing electrons on the right hand side, okay, and we can see here that Mg lost 2 electrons. We then go to chlorine. So we draw out the chlorine again, okay, and we go Cl2. And once it goes to the magnesium chloride, that is 2 chlorines bonded to 1 magnesium. So 2 chlorines. Now, they've also changed from chlorine here, so chlorine, to chloride. Okay, so this is a Cl- ion because it's ionic. And there are 2 of them. So I put 2Cl-. Now, to go from here, which has no charge, to here, which is minus, I must have added 2 minuses because there are 2 minuses here, and that means I must have added 2 electrons. Now, that means when I look at both of these, oxidation is here. So this is oxidation. Okay, and the bottom one is gaining electrons, and therefore is reduction. And because we have both of these happening in the same reaction, we can then just call this redox. And therefore it's a redox reaction. Our next common example of redox reactions is magnesium plus oxygen goes to magnesium oxide. That means you have Mg plus half O2 going to MgO. If we look at the charges on here again, you've got 0 for an element, 0 for an element again, and then we've got 2 plus for the magnesium and 2 minus for the oxygen. If you put that into half equations, you can see that Mg goes to Mg2 plus 2 electrons, lost 2 electrons, therefore it is oxidation. We then go to the oxygen. The oxygen has got to go from O2 to O2 minus, therefore must have gained 2 electrons, therefore it's reduction. And that's the way we would have normally done oxidation and reduction again in GCSE. Now we're going to do oxidizing and reducing agents next. This can become quite confusing, so I would recommend to you that you take it quite slowly when you're thinking your way through this. An oxidizing agent will become reduced So if you think about that, it will gain the electrons from something else, and that something else then loses electrons. So it causes the oxidation of the other element. If we've got a reducing agent, it will become oxidized. It will lose its electrons so that something else can gain. So the reducing agent is causing gain of electrons in something else. Now let's look at this in an example. We've got copper sulfate plus iron goes to iron sulfate plus copper. If we turn it into its ionic equation first, okay, we can do that by looking at the charges, and we can see that sulfate is 2 minus, and that's an ion we need to remember. So if you look at sulfate 2 minus, the copper must be 2 plus, and we apply this rule all the way across, and we can think of the right charges, knowing the ions like sulfate, and knowing the elements are neutral. We then take out our spectator ions. SO4 2 minus is the same on both sides, so therefore we take it out. Once it's gone, we will then do our ionic equation, and then we can split it into our half equations. So let's just look at copper to start. So copper is going from copper 2 plus to the element copper, and that means it's gained 2 electrons, and then the iron has gone to iron 2 plus 2 electrons. So it's lost 2 electrons, the iron, and the copper 2 plus has gained 2 electrons. That means that the copper has been reduced, the electrons have been gained, and the iron has been oxidized because the electrons have been lost. Now if you apply our rule here, an oxidizing agent gains electrons is reduced. So that must mean the copper is the oxidizing agent. Okay, if we look at our reducing agent, that loses electrons, is oxidized, so therefore that must be the iron. Be really clear when you do this that you refer to the actual, the correct ion or element. So copper 2 plus and Fe. Right, let's look at another example in terms of redox and a displacement. So if you add chlorine water to aqueous potassium iodide, as you've got here, we can do exactly the same thing. We can turn it into an ionic equation. But first, let's just remind you of the colours, because you need those for the course. And pale green for chlorine, as you can see, and dark brown for iodine when it's both in water. But let's turn it into that ionic equation again. Okay, so we need to do the charges, and we are doing all of those now. And you can see that I've looked at the elements, put 0, and I have looked at potassium always being in the group 1, so therefore 1 plus, and iodide in group 7, so therefore 1 minus, and the same with chloride across the way. So if we get rid of our spectator ion, okay, which is the potassium this time, you can see that we can then split it into half equations. So the chlorine, so this chlorine here, 2 electrons added, and therefore we've got 2 Cl minus, and then the iodide has lost 2 electrons. So if we apply our rules again, let's look at the oxidation and reduction. So that means the chlorine must be reduced and the iodide must be oxidized, okay? And therefore, if we're thinking importantly about oxidizing agent and reducing agent, the oxidizing agent must be reduced, okay? So we can see the chlorine is reduced, so that's our oxidizing agent, and the reducing agent must be oxidized, so therefore that is our reducing agent. We're now going to move on to the more A-level subject within, because a lot of what we've done so far you would have done hopefully in your GCSE. So why do we use our new term, oxidation numbers? I mentioned it at the start of the video, and the reason why is because it's very, very, very difficult to find out where electrons go unless you can assign an oxidation number. An oxidation number is often the same as a charge. It's very easy to do if you have something like an ionic compound where you know the charges and everything like that. But if you look at all of these, this is the most common example where oxidation numbers is so, so important. If you look at water, water is actually covalent. As far as you're aware at this stage, okay, there's no charges there. So therefore, how do I know whether the electrons have been lost from the hydrogen or gained by the oxygen? Because the H2O is covalent. Okay, and because the H2O is covalent, don't have any ions. So therefore I don't have any charges to go from. And some elements have multiple charges. So you may have common transition metals have multiple charges that go across, and therefore I can't just say, well, it's always going to be this, it's always going to be that. Okay, so it's really important that therefore we have another system of assigning whether electrons have been lost or gained, and that another system is oxidation numbers, also known as oxidation states in some places. Okay, but we'll refer to them as oxidation numbers. Now the rules for assigning, once you've done them a few times, hopefully will be quite simple. So first one, in simple cases the oxidation number is the same as the charge on the ion. So most of the time, and this is actually really common, is that the oxidation number is just the same as the charge on the ion. Now all elements have an oxidation number of 0, which is the same as what we've discussed. Okay, and in compounds all the sum of the oxidation numbers is 0. So if you have an all compound that's neutral, for example if you have sodium fluoride or something like that, or carbon dioxide, they're neutral normally, so the sum of all the oxidation numbers is 0, just like the sum of the charges, so it's the same thing. In a polyatomic or molecular ion, the sum of the oxidation numbers is the overall charge. And we're going to go through examples of each of these, so do not worry about remembering each individual one. Now the way to remember all this is 1, 2, 3 for Hockel. Okay, 1, 2, 3 for Hockel. It really works very well, okay? So if you've got group, that means group 1, 2, 3 are fixed, okay? So what you can do is, if you go in order and you go priority from the left to the right, so if you go to a substance and you've got 1, 2, 3 for Hockel and you see you've got a group 1 substance, you know it's going to be, if it's in 1, it's fixed. Now what do I mean by fixed? I mean that the charge, as we've got in rule 1, is the same as the oxidation number. But let's show you how to write all this down and do some examples. Okay, so during the next few slides, all our rules are going to stay on the right hand side. And we're going to do each one in turn and show you what that means. So first one, in simple cases, the oxidation number is the same as the charge on the ion. Okay, so we are going to do sodium chloride to start off with. So if you look at sodium chloride, okay, so we've got sodium chloride, and then we look at this and we go 1, 2, 3 for Hockel. Well, there's 1. Okay, so there is 1. So what we can do there is say, right, group 1 all have 1 plus ions. So that means, and this is the important change, if you're doing oxidation numbers, although the charge is the same as the oxidation number is the same as the charge, if it's an oxidation number, we switch round the charge. So what that means is, normally you would say this is a 1 plus ion, and you would say this is a 1 minus. If we're referring to it as oxidation numbers, it's going to be plus 1. It's going to be minus 1. Okay, so these are oxidation numbers because we know that the plus is first and the minus is first. These are charges. Okay, so that difference here between a charge, okay, and an oxidation number, okay, is really important, because if you get them the wrong way round, you will get the wrong answer in an exam. These are oxidation numbers, okay, and these are charges. So if we look here, if we use 1, 2, 3 for Hockel again, we go 1, sodium is group 1, therefore we know it has the same oxidation number as its charge, so therefore that's plus 1, and then we can work out the chlorine from that, because if the overall molecule is neutral, or the compound is neutral, now that means that the chlorine or chloride must be minus 1. So you need to work out oxidation numbers relative to the one that you've found out from 1, 3 for Hockel. So let's have a look at that again with a different example. And the different example is going to be calcium fluoride. So if we look at calcium fluoride, we're going to go 1, 2, 3. Well, 1, 2, 3 for Hockel. Okay, group 2 calcium. So So we've got calcium, which is a group 2. Normally it's a 2 plus ion. So if it's a 2 plus ion, it has an oxidation number of plus 2. Okay, we can then work out the oxidation number of the fluorine from this point, or the fluoride. Now you probably guessed that it's -1 because the fluoride ion is in group 7, it's -1, but let's not do it from the charge, let's do it from the fact that we assigned the calcium first. That means if the calcium is +2, the whole thing is neutral, and there are 2, really important, there are 2 fluoride ions there. That means each one must be -1. So that means this totals up to +2 and -2, and therefore is neutral. Okay, so this is your way of saying 1, 2, 1, 2, as in this is in group 2, so therefore it must have the same oxidation number as the charge. But remember, the plus comes first, the minus comes first, if it's an oxidation number. And then you can use the fixed one, which is the calcium, to find out what the fluoride is. And I go for our last one, okay, and our last one is going to be Al2O3. Okay, so we're going Al2O3. We're going 1, 2, 3 for Hocker. 1, 2, 3. 3. Aluminium is in 3. Okay, so that means it must follow the rule at the top. The oxidation number is the same as the charge on the ion. The charge on the ion, because it's in group 3, is 3 plus. Okay, so this is +3, but there are 2 of them. So okay, so I will go +3. Okay, and then that means there's a total on this side of -6. So +6. And because this is +6, that means I need the oxygens, or the oxide ions, to also equal the opposite, which is -6. So this down here is +6. Okay, so that is +6. So I need the other one to be -6. I've got 3 of them, so therefore that means we will do -2, -2, -2. That will equal then -6. And that means the oxidation number of the oxide, or the oxygen, is -2. The oxidation number of the aluminium is +3. Please don't confuse, and this is the one that happens the most, is that people, for example, think that the total is the oxidation number. It's not. You just use the total to work out the rest. The oxidation number is this number here, +3 or -2. It's the individual oxidation number of the element. We have 2 elements here, therefore the total is different to the oxidation number, which is +3, and the oxidation here, which is -2. So we've gone over the following rules for assigning oxidation numbers. So we've looked at the oxidation number as the same as the charge, using 1, 2, 3 out of 1, 2, 3 for Hockel. Okay, and then in compounds, all of the sum of the oxidation numbers is 0. So we did that, all the sum was 0, so we used that to work out the unknown. Okay, and the unknown is often not in 1, 2, 3 for Hockel. Okay. The ones in 1, 2, 3 for Hockel that actually can change oxidation number, or the ones that you come across most regularly, are going to be chlorine, and a very occasional example of oxygen. Now, if we look here, we can see that polyatomic ions. So how do we do this? So polyatomic ions are going to include a rule. So the rule that we're going to look at also is the Roman numeral. So a Roman numeral is used to indicate the magnitude of the oxidation number of an element. This is used when it may be ambiguous. So for example, lots of elements like nitrogen, like chlorine, they can have changeable oxidation numbers. So therefore, we need to find out what they are from the name of the substance. So let's look at nitrate 3. So nitrate 3, all nitrates are NO3 are minuses. So we've got NO3 minus. If that is the case, what we can do is we can say, if we look in polyatomic or molecular ions, the sum of the oxidation numbers is the overall charge of the ion. So the overall charge of the ion is minus. So we use 1, 2, 3 for Ha, and then O. So we've got O. Okay, and that means the oxygen must have the same charge as its ion, okay? So that the ion of oxygen is minus 2, is 2 minus, so therefore this will be minus 2, and just to do the balancing here, it's 3 of those, okay? And then that means, if that's the case, it has to add up to a minus overall. So that, if you think of that as minus 6, it's going to add up to a minus overall. That means on the left it must be plus 5. Okay, and because it is plus 5, we're going to call this nitrate, and we're going to call it nitrate 5. Okay, so nitrate 5. Now we're going to do another one, which is a nitrate 3. So nitrate 3 is NO2 minus. Notice the oxygen has changed. If I then go for the 1, 2, 3 for hot O, so that means it's fixed to the same oxidation number as its ion. So therefore that would be minus 2 minus 2. Has to add up to minus overall, so therefore that must be plus 3. Because that is plus 3, I'm going to call this nitrate, and I'm going to call it nitrate 3. And there's my Roman numerals. So my Roman numerals here, 3, 5. And all it does is indicate the element that can have a variable oxidation number, and you use 1, 2, 3 for Hockel to basically find out what that is. Now, 1, 2, 3 for Hockel and oxidation numbers and such and so forth can also be used to find out a couple of exceptions. So we're going to talk about a couple of exceptions now. Now the exceptions that we talk about, which you must know about, are H2O2, okay, and sodium hydride. So they're required examples. So if we look at H2O2 and we go, right, okay, here we have 1, 2, 3 for H. So the H comes first, okay? So therefore that must have the same oxidation number as its ion, so +1, +1, which means in this case, if the whole thing is neutral, okay, that oxygen must be -1 and -1 because there are 2 oxygens. So the oxidation number of oxygen here is -1. It's the only example that we really do in A-levels that you have -1 as the oxidation number of oxygen. We then do the next one and we go 1, 2, well, 1. Sodium is in group 1, so therefore that's going to have the same charge, which means hydrogen must be -1, which means this is an example where hydrogen is different from what it normally is. Okay, and this is an example where oxygen is different from where it normally is. We'll just do a couple more examples, and we'll flip back now and we'll see. We'll look at another common example of where the oxidation number changes. So those examples are something called chlorates. Chlorate, 8 meaning with oxygen, and they're all minus. Okay, and we have 2 chlorates here. So we're going to go ClO and ClO3 minus. Okay? So I want you to look at those and start thinking before I even say, what are the oxidation numbers? Go through 1, 2, 3 for Hockel. If I'm going through 1, 2, 3 for Hockel, hopefully you're starting to get that point. Here, it's the O this time that comes in. Okay, so therefore -2, okay, which means it has to add up to a minus overall, so therefore that must be a +1. Okay, and then we go to the chlorate here, and we got 3 of these. Okay, and that is 3 of those, so -6. Okay, adds up to that must be +5 overall. Okay, which means that we have chlorate, and we have chlorate 1, and we have chlorate, and we have chlorate 5. Okay, so chlorate 1 and chlorate 5. So we've done 3 different examples on here. We've got the nitrates, which can have variable oxidation numbers on the nitrogen, which you now know from Roman numerals. You know what the oxidation number of the nitrogen is. We've then gone through to our two other examples where you've got H2O2, a very uncommon oxidation number of oxygen, a very uncommon oxidation number of hydrogen sodium hydride. And then we've got our chlorates, again, where you can see the chlorine changes oxidation number from +1 to +5. Again, we've got our Roman numerals that are working there as well. So we're now going to try and use all four of the rules in doing an exam style answer for a couple of equations. So we're going to do the oxidation number as the same as the charge using, remember, 1, 2, 3 for Hockel. Okay, and all elements having an oxidation number of 0, and in all compounds the sum is equal to 0. And lastly, the polyatomic or molecular ions, the sum of the oxidation numbers is the overall charge. So we're going to do it with this equation right here. I'm going to show you a slightly shorter way of doing it than you've done it before. So what I recommend you do is I recommend you look at the equation right here and you just start applying the rules. So you're going across. So this is Mg, so it's an element. So therefore I'm going to put it as an oxidation number of 0. And then we use 1, 2, 3 for Hockel. And we know that from 1, 2, 3 for Hockel, none of the H appears before oxygen. So therefore it is the same charge as its ion, so that's +1. Use the same rule for the oxygen here because that appears next in for Hockel, so that's got to be the same as its charge, so that oxygen is -2. And that leaves us space here to work out our nitrogen, and our nitrogen therefore is +5. Okay, we'll then apply the same rules over here. Okay, for our magnesium it's +2, again using 1, 2, 3 for Hockel, and then +5. And then -2, and then lastly 0. Okay, so we're roughly putting them over the top. Okay, and you would do that. So remember, I'm doing it in order. So here's magnesium, here's the hydrogen, here's the nitrogen, here's the oxygen. Let's start again. Here's the magnesium, here's the nitrogen, here's the oxygen, here's the hydrogen. Okay, so we've got all of those, and then we start working it out. So the important bits are, let's work out which bits have changed. So I'm going to underline the bits that have changed. So you can see here the hydrogen has gone from +1 and it's now at 0. So we're going to, that's changed. So we're going to use that. And then we go from the magnesium, which is 0, going to the +2. So you can see there's some changes here. So when you see the changes, that's when you start needing to draw it out. So in terms of the magnesium, all we have to say is that the magnesium is going to go from 0 to +2. Okay, so loses 2 E minus 0, 2, and that's what we have to do. We have to say, so look, that's because it's going from 0 to +2. Okay, and then we can say from that, if it's going from 0 to +2, that's losing electrons, therefore that is oxidation. We then go up to the next one that's changed, and we see the next one we've changed, we highlighted was hydrogen. Okay, and we go hydrogen at that point, and we say gains. And again, we look at what's changing. It's going from +1 to 0. Okay, so from +1 to 0. Okay, and that means it gains 1 E minus, and therefore if it's going from +1 to 0, that means it must gain 1 electron, so therefore reduction. Okay, so oxidation reduction, so redox reaction. We then go across here and we say, right, it's been oxidized, therefore it must be the reducing agent. Okay, so that's your reducing agent, and then underneath we say that if it's been reduced, it must be the oxidizing agent. So we're using a lot of information and pulling it all together in these equations. Right? And really important that you put all of this information in an exam. So when you do your exam and you're asked a question like this, these are actually they're not slightly nicer questions because they're quite ordered. Just get used to doing these equations, get used to saying what loses, what gains. Don't worry about, at this point, if the electrons don't match. Okay, when you're talking about this type of question, The electrons will match if you use the balancing in the equation, but we're just looking at individual elements. So we don't worry for the minute in terms of this equation. So we'll go on to our final example where we just show you a structured exam answer. And we're doing the same equation, but with a different acid. So what we have to do, the question you would be given would just be, can you describe whether this is reduction or oxidation in terms of electrons? Okay, so we're going to do that. So here we have magnesium, which is 0, follows all elements have an oxidation number of 0. Use for 1, 2, 3 for Hockel to assign hydrogen and oxygen, and then that allows us to find out that sulfur is +6. We do exactly the same on the other side, okay, and we've got all of these oxidation numbers assigned. Then we go from here, and we only write out the ones that have changed, okay, and if you've got a pencil, I'd rub out the rest, okay. And then I just put arrows going saying what's happened, so 0 goes to +2, +1 goes to 0. And then I write this down systematically. So there's 3 parts to your answer. The first part, as I did in the last slide, first part is to say whether it loses or gains electrons and how many. And then we say the oxidation number change, and then we say whether it's oxidized or reduced. Okay, so here we have magnesium loses 2 electrons, goes from 0 to +2, loses 2 electrons, so it's oxidized, and so is the reducing agent. Hydrogen gains 1 electron, goes from +1 to 0, it's reduced, and therefore is the oxidizing agent. So make sure you've got those 3 parts to your answer. What's happening with the electrons? What's the oxidation number change? And then label it with oxidation or reduction or reducing agent and oxidizing agent.